please keep quiet and sit down. So I'm going to do number 9. Number 9 says, given the point, so I'm going to start with points and then go on to 2-dimensional regions and then go on to 3-dimensional regions. Given the point Q, root 2, root 6, root 2, in rectangular coordinates, so that's x and that's y and that's z, express Q in cylindrical and spherical coordinates. Okay, so now, even though at the top here I've written my points, still even when I've gone away from rectangular coordinates, I've written them in brackets. In general, I'm not going to do that. Question at the back. 2 root 2, yes, thank you very much. I copied incorrectly from the handbook. Thanks very much. So even though I kept that sort of brackety way of writing the points, even when it's not x, y, z, in fact, when we write a point in, or when I, in this course, write a point in a coordinate system that isn't rectangular coordinates, I actually tend not to use the bracket notation because it's confusing. If you see open bracket number, comma number, you tend to think that's rectangular coordinates and it's x, y, z. So if I'm writing a point in cylindrical or spherical, I'll be very explicit and I'll say r equals this, theta equals that, so it's quite clear what the components are. Just as sort of a shorthand, I've bunched them together in brackets at the top there. Okay, so now we want to write that in cylindrical and spherical, so we need to figure out where that point is. So, that point sits up here with an x-coordinate of root 2, a y-coordinate of root 6, and a z-coordinate of 2 root 2. Okay, there's z, there's x, there's y. Okay, I'm going to draw just my xy plane. So here's the sort of projection of Q, so that's Q projected onto the xy plane. And that's a root 2, and that's a root 6. Okay, which makes it fairly easy for us to work out what r and theta are. Okay, r is going to be that, and then theta is going to be the angle between the positive x-axis and that line. It's quite funny, on the screen that's a fairly dark green, but up here it's not. Or rather on, yeah. Interesting. Okay, so what I notice, now you can get out your calculator and work it out with your calculator if you want, but what I'm noticing is that this is basically my 1 root 3, 2 triangle scaled up by a factor of root 2. Because if I just take that and times it by root 2, and I take that and times it by, actually I shouldn't have drawn it in that orientation, should I? Let me change the orientation. And nothing I did there was wrong, I'm just going to choose to draw it like that. Am I going to draw it like that? No, I'll go back to what I had. That's my 1 root 3, 2 triangle scaled up by a factor of root 2. Because if I take each, my picture's too small to write that in. But basically, you're taking that triangle and you're taking each side and you're timesing it by root 2. So 1 times root 2 is root 2, root 3 times root 2 is root 6, and so my hypotenuse must be 2 root 2, so, back to the pen, here we go, that must be 2 root 2, and the angle in there is going to be what? This little theta angle? Is it 30 degrees or is it 60 degrees? Come on, you know your special triangles. Is it just too early in the morning, you haven't had your coffee yet? You just haven't had your coffee yet. It's 60 degrees. Which in radians is? Pi over 3. Oh my goodness, you're sleepy. Wake up. Come on. It's bright red. Okay, it's supposed to wake you up. Hey, have some coffee before you come to class, or one of those fizzy vitamin C things or something. Wake yourself up. Splash your face with cold water. Which in Cape Town basically means just go outside and look up at the sky for a bit. I had some first years once a few years ago. You could please be quiet. They were first years, they were new to Cape Town. They weren't familiar with Cape Town, and they were very sad, and they said when you apply to UCT and you get brochures, in the brochures the sun is always shining. The truth of UCT was not apparent in the brochures. Cold and wet. Okay. So let's have a look. So that's given us our R, has given us our theta, and our Z comes free of charge for cylindrical coordinates because the Z is the same as the Z in the rectangular. So in cylindrical, R is 2 root 2, theta is pi over 3, and Z is also 2 root 2. Okay, so now let's do spherical. Now for spherical, my rho is the length of the line that goes from the origin to the point. So the way I'm going to work that out is I'm going to look at this triangle that I've just drawn in. If you drop a perpendicular from Q down to the XY plane, it's perpendicular to the XY plane. So I've drawn in a little 90 degree there. Now, on a flat picture, that doesn't look a lot like 90 degrees, but it is 90 degrees because that little line, that little short line over there is on the XY plane, and this line over here is perpendicular, so that is 90 degrees. So I have a nice little 90 degree triangle going on there, with Q at the top of it. There's 90. Here's my 2 root 2, which is R, which I've already worked out. Here's my 2 root 2, which is my Z, which I was given. They're equal, which must mean that this is pi over 4. And if that is pi over 4, then so is this pi over 4. Could you please be quiet? Which means, so this one that I've drawn over there, that's my phi. Okay, it's not the one that's inside the triangle, that's the phi, it's the one that's outside. They happen to be the same in this problem. And then my rho is going to be the hypotenuse of that, so what is that? Square the two sides, and that'll be a 4 and a 2, it's 8, and 8, and so it's 16, so it's 4. So the length of this line is going to be 4. So in spherical coordinates, my rho is 4. My theta is the same theta that was in cylindrical, so I've already worked it out. And my phi is pi over 4. You try. Do number 10. Okay, I'm just going to write here, you try 10, and then I'll scroll back up again. So you can see all my little pictures. Okay, so that is taking a point that's in one coordinate system and turning it and just writing that point in a different way. We're very rarely going to do that. What we're going to more likely do is change entire regions. Because when you do a single variable integral, so you've got an integral of x squared dx, whatever, and it's a definite integral, and in this course we're only doing definite integrals. And it's a definite integral that integrates from a to b, where a and b define an interval on the x-axis. So your region of integration is a set of real numbers that are on a single dimension. In this course, we're going to be doing double integrals, which have two integral signs. We're going to do single surface integrals, which also have two integral signs, but they're slightly different. And we're going to be doing triple integrals, which have three integral signs. When you have two integral signs, the region over which you are integrating is a two-dimensional region. So it's something you can actually shade in with a pencil. It's not just an interval on a number line. And then with triple integrals, surface integrals are similar to double integrals in that sense. And triple integrals, we're going to be integrating over three-dimensional regions. So things like spheres or rectangular blocks or something. So we need to be able to describe regions in appropriate coordinate systems. So two-dimensional and three-dimensional regions. So let's look at two dimensions. And I'm going to simply demonstrate with an example. I am going to do number 12. Okay, so number 12. It says describe the following regions in polar coordinates. Okay. Because they're two-dimensional, so polar. So we're not going to use the term cylindrical or spherical when we're talking about two-dimensional regions. Although in a sense, polar coordinates and cylindrical coordinates are kind of the same thing, just with, you just ignore the z component if you're looking, or you set z to 0. So cylindrical and polar are kind of the same thing with just the z set to 0 for polar. Okay, the region in the third quadrant, inside the circle, this thing. Okay, so I'm starting off with a simple one. We've got x squared plus y squared. Please keep quiet. If I'm talking, I prefer you keep quiet. Because even if you don't care what I'm saying, the person sitting next to you might. You're welcome to not care about what I'm saying, as long as you manage to get on top of the work. Okay, it says the region in the third quadrant inside that circle. Okay, so that's the region that we're interested in. Now, an important thing about describing regions is you're always going to say the region, however you're describing it, whether it's in terms of polar or rectangular or in 3D, if you're talking about cylindrical, you're always going to have inequalities. Almost always going to have inequalities, where you're going to say this particular component, the r or the rho or the theta or whatever, goes from here to there, and so you're going to write it with inequality signs. Or I suppose you could write it as element of a set, but we usually write it with bigger than, smaller than. Okay, well actually no, I tell a lie, there is no usually. Sometimes we write it as element of an interval, sometimes we use inequality. However the mood strikes us. Okay, so polar, we're going to be talking about r. We're going to be talking about theta. Okay, so now excuse me while I belabor this just a little bit, but basically we're thinking of this region as containing infinitely many points, and we're going to try and describe where those points are. Okay, so we're going to say, this one is a particularly easy one. And it's like that. All of those points fall between r equals 0, which is the origin, and r equals 2, which would be the edge of the circle. And that's for angles of theta, for values of theta that are between pi and 3 pi over 2, and that is what puts us into the third quadrant. Now, when I'm doing these things, okay, there I drew lots of dots, but what I often do is I often draw what I call a ray, and I'll draw a line from the origin through the region to the edge of the region. And I'll think to myself, okay, I'm interested in points along that little ray. How far do those points get from the origin? And here is a very important question. If I draw a different ray, am I going to get a different answer? Is the furthest point on the ray, the end of the ray, the bit where it bumps into the edge of the region, is it going to be a different distance from the origin depending on where I draw it? In this question, the answer would be no. I can draw that ray anywhere, and it will just be a radius of the circle, and all radii of a circle are exactly the same length. So it doesn't matter where I draw that little black line, the length of the black line is going to be the same no matter where I draw it. And that means that r is not a function of theta. If the answer to the question was yes, the ray will be a different length depending on where I draw it, then r is a function of theta. Okay, because how far you can get from the origin depends on what direction you go. That is very, very important. Okay, now I'm quite a visual person myself. Everybody learns in different ways and sees mathematics in different ways. Perhaps you're a more algebraic kind of person, in which case you can solve for, in this case, it's actually such a simple one that the algebraic way is not terribly useful. Okay, there's always a geometric way of solving these things and an algebraic way. That's the geometric way, you draw a picture, and in my case, I like to draw little rays and to work out how long the ray is, etc. The algebraic way would be to actually take the equation of the curve that's describing the edge of your region and take that equation and change it according to the little relationships you know about the coordinates. So for instance, here we've got x squared plus y squared equals 4. We know that in polar coordinates, x squared plus y squared is r squared. So we could just write that as r squared equals 4. Therefore, r equals 2, because r is positive, and that gives us our largest value for r. Okay, now, this is such a simple problem that there's not much to be gained. There are some problems where manipulating the equation rather than drawing the picture can actually get you to the answer a little bit faster if the picture is actually quite a complicated one. And the one I'm thinking of particularly is 15C, and I think 15 is probably assigned to a tutorial. Is 15 assigned to a tutorial? It is indeed. And 15C it's quite a tricky one to do with the picture. It's actually easier to do algebraically by manipulating the equation. Okay, but back to 12. That was 12A. 12B, a little bit trickier. The region inside the upper semicircle of x squared plus y minus 1 squared equals 1. So let's draw that. That is a circle of radius 1, centered at the point 0, 1. So when I draw the picture, it's going to look like that, and we're just interested in this top half. Okay, we're going to work quite a lot in this course with circles that do that. Circles that have been shifted off the origin, and yet the circumference passes through the origin. We're going to do that with spheres as well. Spheres that have been moved off the origin, usually upwards, but maybe sideways, but the actual surface of the sphere still passes through, or the sphere itself passes through the origin. Well, it's quite a common phenomenon in this course. Okay, so what I'm going to do is I'm going to draw a ray. There it is. And I'm going to ask myself, is that ray going to be a different length depending on where I draw it? And the answer is yes, it will. Because if I drew it with quite a smallish angle, well, if I drew it with a very small angle, I'd miss the region entirely. But if I drew it like it was there, it wouldn't be terribly long. But if I drew it straight up, of course, it would get to 2 units. But there's no way it's getting as far as 2 units if I draw it over here. So r is a different length depending on where you draw it, which means that r is going to be a function of theta. Because how long it is, the maximum extent of r depends on where you draw it. In other words, it depends on theta, so it's a function of theta. If something depends on something, then if A depends on B, then A is a function of B. It's the mathematical way of saying depends on. Okay, so what I'm going to do, actually I'll stick with black for now, I'm going to draw in a couple of triangles. First of all, there's a little weeny triangle down there with a little 90 degree. I know that that vertical distance over there is 1 because my radius is 1. And so I can work out what this distance is over there. This little hypotenuse I can work out using this little 90 degree triangle. Why do I want to know this hypotenuse? Because over here, in this one over there, my minimum value of r was 0 because my region was touching the origin. There were dots in my region that were sitting right on the origin, whereas that's not the case here. The closest points to the origin, or rather let's have a look. Yeah, the closest points to the origin are the points that are sitting along that bottom line, that horizontal line. So I want to know what that little hypotenuse is. But similarly, I also want to know what the whole length of the line is. And for that, I will draw a different triangle, which will look like that. Has the 90 degrees in a different place. And I know that's 90 degrees because I know my circle geometry and I know the angle on diameter is 90 degrees. I will callously and cold-heartedly assume that you know all the maths that you have ever done. So I'm going to assume that you know all your first year maths, that you know all your trigonometry, that you know all your geometry, that you know how to factorize, all of that lovely stuff. Log laws, maybe here and there. All of that stuff, I'm going to assume that you know. If you don't, catch up. Spend the weekend thinking, gosh, what have I done in maths? Maybe I should spend a couple of hours relearning it. Okay, so I've got 2 triangles going on there. I'm going to draw them separately here. There's that one. And there's this one. I know that's a 2, that's a 90. I'm going to call that R1 and R2, and my R that I'm looking for is going to lie between R1 and R2. R1 is the shortest that R1 describes the closest that points can get to the origin, and R2 describes the furthest that points can get from the origin. And so those are going to be my two limits on my inequality. Okay, but there's no angle. There's no angle. Where's the angle? The angle's here, which means the angle is here, which means the angle is here. Alternate angles. Angles between parallel lines. A little bit of, okay, makes a Z, so that's theta, okay? So that uses your parallel line stuff, which you do in what? Grade 9? When you do the parallel line geometry? Grade 8 already. And then here, we know that those two angles over there add up to pi over 2, right? But we also know that those two angles over there add up to pi over 2. So it must mean that that angle and that angle are the same angle. Okay, alrighty then. This sort of picture, you're going to draw, I don't know, if any of the repeat students want to put their necks out there, you can estimate. You're going to draw this picture or a very similar picture 20 times? 30 times? Before the end of the semester. So you're going to get very used to knowing where theta goes. Alright, so let's do some little calculations. We know that, where's theta? Theta's over there. So opposite over hypotenuse is sine theta. So R1 is cosec theta. Okay, and then in the bigger triangle, let's have a look. R opposite over hypotenuse is sine theta, so R2 is 2 sine theta. And so we can conclude that our R lies between cosec theta and 2 sine theta. Again, you're going to do this. By the end of the semester, you're almost going to be able to just guess that answer, or if it's a slightly different circle, you'll be able to. You're going to do this a lot of times. Okay. If this looks a little bit, I'm going to keep moving. I can't stop for too long. I want to do 12C. But if you think, gosh, I'm actually not sure what's going on here, take the time before you go to sleep tonight to understand 12B. It's very important. Okay, but that's all. Let's talk about theta. Theta's a little bit easier. If I imagine almost like, so it's not like a clock because it's going anti-clockwise, but imagine a ray that's kind of ticking round. If the ray is drawn really low down, there is no region. Okay, bigger angle, bigger angle, bigger angle. Oh, it'll bump into my region for the first time at theta equals pi over 4. We know it's pi over 4 because that's 1 and that's 1, and so it's nice associative little thing. So pi over 4, we start bumping into region, round we go, round we go, round we go, round we go, round we go. At 3 pi over 4, we run out of region. That describes our region. So that region, described in polar coordinates, is that stuff that I've written in green there. And ultimately, the role in this course, the role that this sort of process will play, will be giving us limits of integration. Those will become our bottom and top limits of integration of an R integral sign and a theta integral sign. Question over there. Can I explain the angle? So, in a sense, what you can say is that R is bigger than this and smaller than that. So R is bigger than this function of theta and smaller than this function of theta. For values of theta, which legitimately fall between this and this. So basically, you can imagine your region there as being lots and lots and lots and lots of little dots. And if you take each little dot and interrogate it and say, what's your theta value? You'll find that those theta values fall between pi over 4 and 3 pi over 4. The little dot that's over there has a theta of pi over 4. And I know it's pi over 4 because that little dot over there sits on that perfect little isosceles triangle, and so I know that these angles are all pi over 4. So that little dot there has a theta value of pi over 4, and then the angles get bigger and then bigger and bigger, and there's little dots inside the region for all of those angles, and I keep going around, and then this last little lonely dot, the far corner, it's the biggest angle. It has the biggest angle of all the dots in the region, and its angle is 3 pi over 4. 135 degrees, but please don't use degrees. This course is entirely calculus. Calculus doesn't work with degrees. I don't want to say degrees. Yes, I can work it out. I'll work that one out. Okay, all right. Well, that one very similarly. Okay, this dot over here also has a little triangle like that. And so I know that that's pi over 4, but meantime I have to add it to the pi over 2 because you always measure your angle from the positive x-axis. So I know that if I drew a line over there, I know that that little angle inside that will be pi over 4, which means that all of that will be pi over 2 plus pi over 4, which is 3 pi over 4. Pictures, the power of diagrams. Okay, all right, there's only 12C to go. 12B is really important. Yep, one page there. Whenever I go to a new page in this sort of journal program, it always jumps, and it can be a little bit startling, but I can always scroll back like that. Okay, 12C, the line x equals 3. Okay, so this is almost kind of like a joke one because we'll very rarely require you to do this sort of thing, but x equals 3, let's have a look. What does the picture of x equals 3 looks like? It looks like that. And how are we going to describe that? Well, you can think of this line as being lots of points that go up and down forever, and x is always 3. And here, the simplest thing really is just to say, well, we know that x is r cos theta, therefore r is 3 sec theta. So that's really an algebraic solution here. If you want a more diagrammatic, you can do that. And there's your theta, and there's your r, and you know that adjacent over hypotenuse is cos, so 3 over r is cos theta, and therefore r is 3 over r is cos theta, therefore r is 3 over cos 3 sec. So you can do a little picture, or you can, this one is so simple, x equals 3, that just fiddling with the algebra is probably fine. So r is equal to 3 sec theta. So in this case, r is not between something, because there's no shaded region there. There's nothing you can color in with your pencil. So r doesn't, if you draw your ray, you don't kind of enter the region and pass through the region and then pass out of the region like you did in the top draw, in either A or B. For any one value of theta, there is only one value of r. So in this case, there are no inequalities. There's a question? Yeah?
All the polar coordinates just like the origin.
Yes. Which can be confusing. So the question was, are we always interested in the origin? Are we always going from the origin when we're looking at polar coordinates? And yes, we are. Which can be confusing if you think of r as meaning radius. So in that one above, the circle had radius 1, and yet we didn't say r equals 1. R was not our radius. R was distance from the origin. And radius and distance from the origin are very similar things when your circle is centered on the origin. But as soon as you shift it off, then they don't bear much resemblance anymore. So yes, always origin. And theta, always positive x-axis. Question?
Yeah, but you didn't draw the ray in 12B from the origin. You drew it from right below the origin.
No, I didn't. Oh, this over here is the origin. Because that's my x-axis. Yeah, no, it's very easy to think of the center of the circle as being the origin. It really is. So I suppose if I'd labeled my axes, it would have been a little bit clearer. Okay, so cool, that's r. So r is 3 sec theta, but what's theta? Okay, question at the back.
What if the line is not like parallel to any of the x and y axes? It has like
Okay, so if it's oblique, then its equation would have had x's and y's in it. And then I suppose what you would have done is you would have simply replaced the x with r cos theta, and replaced the y with r sine theta, and then done your best to make r the subject of the formula. Then you would have got r equals something very jumbled, and that would be your answer, instead of something neat like this. Yeah, good question. Okay, so what's your range for theta? What's the smallest theta can possibly be? What's the biggest theta can possibly be? Can theta be 0? Okay, cool. Good to know. Can theta be pi? No. Then we go straight up in this, and if you draw your ray straight up, you never get a bump into the line. Can it be... No, sorry, pi is that way. Sorry, pi over 2. Oh, can it be pi over 2? Sorry, yes. What did I just say? Oh, pi over 2. Can it be pi over 4? Can it be pi over 6? Pi over 3? Pi over... So what's the rate? Can it be negative? It needs to be negative. Because negative would just mean going measuring this way, which is fine because there's line down this way. But we can't go too far, of course. Minus pi over 2 is going to be a problem. So, of course, I've said let's not talk about degrees, but I'm just going to break my rule almost immediately after making it. Can theta be 80 degrees? If I drew a line at 80 degrees, if I drew a ray at 80 degrees, would it eventually bump into the line? 85? 89? 89 and a half? Somebody said no for 89. 89.9? 90? No. Okay, cool. You're waking up. Yay. Notice what I've done there? There are no equal signs on those inequalities. So if I draw my ray almost vertical, but not quite, it'll have to go a really long way before it bumps into that vertical line, but eventually it will. So I can make my angle as close to pi over 2 as I want, as long as I don't make it exactly pi over 2. So I'm going to actually make pi over 2 my limit, but I'm not going to put an equal sign in there. And there you go. Cool, fun, yes? Yes, lots of fun, right. So it's the end of that period now, but tomorrow I'm going to ask you to do number 13 and 14 straight away. That's how we're going to start the period. And then I will move on to do number 16, which is a 3-dimensional one. And then we're all ready to start space curves on Monday. The horse is still just trotting, by the way. Okay, so I repeat in case anybody missed it. I am perfectly happy to sign 2083s over to 2085 because I'm confident that we will get a larger value.